Hi there, and welcome to this first lesson on Chapter 7 from Further Pure Mathematics 1. We're making very good progress. Seems like only yesterday that I was making a video on Chapter 1. Chapter 7 deals with series, and 1.1 is on sums of natural numbers. And we begin just with a reminder of sigma notation. So sigma is the Greek letter S, the capital S. It's the sign that becomes the integration sign. And in both cases, it just means sum of, it means add together. If ever you see a sigma, it is asking you to add together a whole lot of things. The lower limit is at the bottom, so you're starting at r equals 1, you're finishing at r equals 3, substituting into there. Okay, have a go at doing this yourself very quickly. Pause the video. Okay. So putting 1 into the expression, you get this. Putting 2 into the expression, you get the middle one. Putting 3 into the expression, you get the end one. Tidying those up, you get 5 plus 11 plus 19. And in total, that gives you 35. Have a go at writing this down. The upper limit isn't written down. Now, you can write down the beginning. You can't write down the middle, but you can write down the last two terms. So have a go at doing that. Write down the start, leave out the middle, write down the last two terms. Pause the video. Okay, so it begins 1 squared plus 2 squared plus 3 squared. The last term will be n squared. It's often useful to write down the penultimate term. In this case, that would be n minus 1 squared. Sometimes there is no final term. If that's the case, you would write down the first few terms, and then those dots indicate that the expression does go on forever. Two important sums you should know. The first one looks trivial, but is used quite a lot. If you're adding from 1 to n, the number 1, that means you're adding 1 together n times, which is just n. Adding together from r equals 1 to n, just r on its own, is adding together the natural numbers, 1 plus 2 plus 3 plus 4, up to n. And the answer should look familiar to you. It's the same idea as you have with arithmetic progressions. Okay, this next example, I think you can possibly do it using what we've just been doing, but I actually just do it like we did the first one. Anyway, pause the video, quickly do this yourself. Okay, so putting 1 in, you get 3 minus 5. Putting 2 in, you get 6 minus 5. Putting 3 in, you get 9 minus 5. Adding those together is minus 2 plus 1 plus 4, which gives you 3. This next example is more important. Have a go at this and try and do it using the second of the formulas that we met just now. Okay, pause the video. So the formula was the sum from r equals 1 to n of r is just n over 2 into n plus 1. In this case, n equals 100. So I'll have a half times by 100 times by 101, which gives you 5,050. This is a very famous example. It is said that the very famous mathematician Gauss, on his first day at school, when he was about 7 years old, along with the rest of the class, he was asked to work out the sum of all the numbers from 1 to 100. The teacher was probably just trying to buy some time. And he immediately wrote down the answer, 5,050, and it's believed that Gauss, by the age of 7, had already intuitively understood this formula. Okay, have a go at the third example. This one isn't so trivial. The thing that's different is the lower limit, the sum from r equals 21 to 40 of r. Have a think yourselves about how we negotiate that. Pause the video, and then when you're ready, start it again. The easiest way to do this is to consider, first of all 40 terms. So if it did start at r equals 1. And then to take away the terms that you don't actually want, which is the first 20 terms in this case. So the sum from r equals 1 to 40, a half of 40 is 20, 40 plus 1 is 41, half of 20 is 10, 20 plus 1 is 21. That gives you 820, take away 210, which is 610. Now, in general, what we've been doing there is the sum from r equals k to n of any function. Work out the sum from r equals 1 to n, then take away the terms that you don't want. Be careful with the upper limit here. So the upper limit will be k minus 1. Those are the terms that you need to take away. Okay, example 4. Have a go at this. The upper limit isn't specified. It's just given us to capital N minus 1. The lower limit is r equals 5. It says only for n equals or greater than equal to 3. Don't need to worry about that, but it wouldn't work if n was less than 3. Have a go yourself. Pause the video. Okay. So the first thing is to split it up like we were doing just now. Say that you'll find all the terms from r equals 1 to 2n minus 1, and then take away the terms that we don't want, which in this instance are the first 4 terms. Then we put in the upper limit in the normal way. So you've got a half n into n plus 1. In this case, n is 2n minus 1, overuse of the letter n here. And adding 1 to that will give you 2n. And then with the second expression, n is 4, so we'll have a half times 4, and n plus 1 is 5. Multiplying out these brackets gives us that. Tidying up all the terms gives us 2n squared minus n minus 10 for the answer. 3 important results. The first one is the one we've just been looking at. The second one is, if you have the sum of 2 functions added together, then you can split it up into 2 independent sums. This also works with integration. If you have the sum of a constant times by a function, you can take the constant outside of the sum, work out the sum, and then multiply by the constant. That also works with integration. Okay, bearing those in mind, have a go at this question. Pause the video. When you're ready, start it again. So first of all, we've split it up into 2 bits because of the plus. And what we've also done is taken the 3 outside of the first sum. The reason for doing that is because these 2 expressions are the 2 expressions that we met at the very beginning that we know a formula for. So the formula for the first one is we'll have the 3 from outside, a half, n is 30, n plus 1 will be 31. And the second expression is just n, which is in this case 30. Tidying all of that up, we get 1395 plus 30. Adding those together, you get 1425. Example 5. It's always nice when they tell you the answer in advance. So you've got to show that this is equal to this. Have a go yourself. Pause the video. Okay. So we split it up just like we did the first question. There's a minus in the middle, so we can split it up into one thing, take away another thing. Both the 5 comes outside the sum with the first one. Also the 3 does with the second expression. 3 times the sum of 1. Again, the reason for doing that is we've got a formula for these 2 sums. A formula that we now use. So in the first case, we'll have 5 times a half, just times n plus 1. And in the second case, we'll have minus 3. And the formula for this expression is just n. I think there's a little bit of factorizing going on there, and the 5 has been put inside the brackets. So that gives us a half times n times 5n plus 1, and then this minus 3n has been factorized into the brackets as well. The reason for doing that is because if you tidy that up, you get exactly the answer that we wanted in the form that was requested. Okay, example 6. Using the result that we've just found, evaluate this sum. Now, just be careful again. Notice that the sum starts at 15. Have a go at this yourself. Pause the video and come back when you are ready. Okay, the first thing to do is to use the formula we were using a few minutes back, which is say, well, if we want to find the sum from 15, we'll actually find the sum from 1 first of all, then take away the first 14 terms because we don't need those. Now, what we're doing now is using the formula. So we're not doing this the long way. We have a formula for this expression. So we are using the formula for that expression, which gets us the answer much, much quicker. Putting r equals 30 into the first one gives us this. Putting r equals 14 into the second one gives us this. Tidying all of that up eventually gets us to 1776. Okay, that is the end of this section. Go to page 119. Have a go at exercise 7a. Thank you for watching. and cheerio.